Okay, so next up is applications of zero-knowledge primitives to gaming from Tarrance Van As at Cartridge.
Thank you. Is there a clicker? Thank you. Awesome. Hey, everyone. I'm Tarrance. I'm one of the co-founders of Cartridge, and for the past about a year and a half now, we've been building fully on-chain games and taking advantage of a lot of the exciting research that you guys have been doing to enable this new medium. And so I'm going to give a little bit maybe of a more of a practical talk here of some of how we're using zero-knowledge proofs and in practice to scale to the amount of compute that meets the requirements of pretty complex games that we're trying to put on chain. And then I'll wrap it up with a few existing open challenges that we're still trying to solve that are necessary to fully realize this idea. So like I mentioned, I'm the co-founder of Cartridge. We've been building tooling and infrastructure in games, primarily on top of StarkNet for the past year and a half. I'm also one of the core developers of Dojo. Dojo is a provable game engine. So it's a game engine where you can implement the logic and the state of your application, and it's written in Cairo, so you can prove those computations, and then you can, and it enables like a whole lot of different types of architectures that allow us to start to expose essentially like the existing server-side infrastructure that had to be centralized to kind of arbitrate like the integrity of the participants in a game. You can now start to remove that and decentralize that. So what are autonomous worlds? So autonomous worlds is a category of these fully on-chain games. It's quite an ambitious objective. It's quite a small nascent field right now of maybe 50 to 100 developers that are incredibly excited about leveraging these new affordances provided by zero-knowledge proofs, primarily like a massive increase in the amount of computation that you can do, and different scaling architectures to basically land entire games on chain so that games can inherit the hardness of the blockchain. You can have games that can live perpetually. They don't have like some centralized server that needs to be operated by a for-profit company. They can be permissionally expanded. You can build architectures that allow anyone to contribute and to extend like the lore of the game and to build new interpretations of it and new experiences on top of it. And so why should this be interesting to you guys? I think there's a whole lot to say about like why on-chain games are compelling from a game developer or player perspective. But for this particular audience, I think like the main takeaway is that the games provide a really low stakes playground for experimenting and deploying these new technologies in a way that there's much less obviously financial and regulatory downside. So, when you're experimenting with privacy technologies, for example, if you want to deploy them into production, as soon as you start touching financialized assets, there's a lot, the scope of what could go wrong increases dramatically. In the on-chain gaming space, where a lot of developers are very eager to apply these things in very experimental, playful ways, that allows you to ship them into production, start playing with them. You can relax some of the constraints around decentralization or censorship resistance and test like isolated pieces of the technology. And it's a concrete use case that people are excited to use today. So what do we need to enable these fully on-chain games? At the end of the day, we kind of want it all. We want fast, cheap, composable, responsive, and private. And obviously, this is not accomplishable within like the single context of a single blockchain. So I'm going to talk a little bit about the architecture and how we can use fractal scaling and how we're using it today to try and enable an architecture that can support a fully on-chain game. And I'll reference a canonical example of a game that I think looks very similar to what an autonomous world could eventually look like, which is World of Warcraft, which was like a massively popular game. It's an MMORPG where basically people role play as different characters, and it has a bunch of different layers to the complexity of the game that map quite well to how we can start to architect the roll-up infrastructure to support these types of games. At the base, you have the accounts, and then you have the in-game economy. The in-game economy has certain requirements where it has like global context. You want to be able to sell and exchange things across everyone in the universe. Is probably less frequent transactions, and they're higher value transactions. Then you have like the general population, like the shared context for maybe a particular part of the map or a particular server or a particular region where there's a bunch of players. They maybe are not like interacting too much. They're doing more social coordination. And then you have things like instances and dungeons where you have participants doing like high frequency interactions with the world, but in a very small context, right? It might just be you and 5 friends, and you don't need to execute this computation, or you don't need to touch the state of the entire world. And so how can we kind of start to scale up the backend for these games using rollups to be able to support these different contexts? So this is where we are today. We have, we, as I mentioned, have been primarily focused on StarkNet. You have like StarkNet Layer 2. It's a significant improvement on top of the existing, on top of like Layer 1 as far as like capacity. You have 10 times faster, 10 times cheaper transactions. You have faster block times, 5 seconds, and then you have composability across the DeFi ecosystem. One of the challenges is it's still not cheap enough, it's still not fast enough, and it's not private. So it is a great layer to support like things like, the marketplace in a game. So in the case of World of Warcraft, you have the auction house, which is, very similar to OpenSea or Uniswap that exists today. In most DeFi ecosystems, it's just like a place for people to transact and trade across the entire universe. And Layer 2, like StarkNet, is a perfect place to support something like this. But to enable like the actual gameplay where you have the interactions that people are doing fully on chain and to have much faster block confirmations and lower latency, we have to scale to the next level, which is Layer 3. And so you have gaming specific rollups, and might be region specific rollups, so they might be located closer to the player so they have lower latency. They might even shard like a particular map into different logical regions based on the population of the people that are participating at any given point in time. And so the great thing about this is, in most cases, we're willing in the gaming industry right now to trade off centralization for throughput and performance. So basically giving up on some of the censorship resistance that you get from decentralized networks, but removing all the overhead that's necessary for for decentralized consensus. And so when you have a game-specific Layer 3, you have a lot more options around the configurability of the node. You can, the transaction cost with this additional level of aggregation up to like, sometimes 100 times cheaper. You can have much faster block transaction confirmations in the order of like hundreds of milliseconds, probably even faster. And it's very easily horizontally scalable. So you can use solutions, and you can use solutions like Herodotus, like with storage proofs to provide access from these game-specific rollups to the shared world state. And you can use things like shared sequencing to allow interactions across these different shards, so allow people to like phase between different rollups. And you have this like pseudo-private, because this is one of the hardest problems with on-chain games, obviously, with exposing the backend is private information, and we'll talk a little bit more about that in a second. But if it's operating by a centralized sequencer, the threat model is at least a little bit better than in a decentralized context where you can't have anyone extracting MEV. You have some trust that you're giving to the sequencer, and you have like, this pseudo-private property. And then, some of the cons is obviously it's less composable with the rest of the DeFi ecosystem. You're in this isolated world. You maybe have latency to step down in the stack or then down to the layer below, and it's much more trusted. And these type of Layer 3 game shards can support this type of interaction. So here in the World of Warcraft, you have, for example, Orgrimmar, which has a lot of people just hanging around. It's where a lot of social coordination happens, and you need like it's very geographically constrained as far as where the participants are going to be. So it's very easy to allocate them to a particular context, but it requires at least like significant more transaction throughput or compute to be able to allow them to all interact with each other. And then you have the next layer, which in this case is like if you're just, the idea is if you're just like in the example of World of Warcraft running a dungeon where it's just you and 5 friends and you're just doing some PvE events, you're completing some series of actions and you're defeating a boss and you want to prove to the rest of the world that you did that, you don't have to do that in the shared context of the entire blockchain, right? Like you can have a specific rollup or, it's not really even a rollup in this site. There's different, I think, constructions of how you can sequence the transactions, but the practical implication is that you can basically move this computation fully off-chain. No one cares about like how you accomplish the goal. You just want at the end of it to prove that you accomplished some goal that you can settle to the layer below, and then you can unlock the rewards for accomplishing that. This is, I think, like ultimately the way to scale blockchain games, to like allow a lot of people to play their own little instances, potentially, even single-player games locally, and then just decide like, oh, if this is a good outcome, I want to prove it, generate the proof, and then settle it on chain and unlock the rewards in the global context. And so this is, an example in World of Warcraft. If you're in an instance, it's just you and some friends, 5 of you, and you're fighting some monsters, and the objective, obviously, kill the boss, and then once you kill the boss, you get some loot and for your character and improve it over time. But it does introduce some additional challenges, which I'll touch on in just a moment. So in this, the benefits here are obvious, like it's cheap and potentially free if you're just doing this by yourself, improving it locally on your computer. The interactions can be very fast, low latency, and it's very efficient to settle the outcomes. You don't need to care about all the previous history of like how people accomplished a particular objective. You just want to know, like they just want to convince you that they did it, and that's very succinct to do with, obviously, with snarks. Another practical outcome is that you don't have to share the strategy of how you did it, right? Like that can remain private, like how you accomplish the goal can still be opaque to others. The cons in this kind of configuration is potentially grindable. Like if you have everyone just doing this on their own, you can just throw a lot of computers at it. You can run a lot of instances in parallel and try and get all the best rewards. And so there needs to be some thought around like game mechanics that fit well into these constraints, as well as what are some approaches that we can use to solve them. So some of the challenges, I mentioned a couple of them. I mean, I think the biggest one is fog of war. Fog of war is this idea, in the research, it's called witness encryption. In games like Age of Empires or Warcraft, it's this idea of there's like, some information that players know, and so you may have a map where your immediate vicinity where you can see, that map, and you have another player and they can see theirs, and then there's some parts of the map that nobody knows, and you need to like contextually reveal that information based on some action. So, as you move troops across a map or a scout across a map, you want to discover resources. And the important thing is that no one should know ahead of time where those resources are. You have to do the work to go and expose it. And some of the solutions that people are working on, I think, there's a decent amount of trade-offs in these, are using secure enclaves and MPC-based constructions. But I think, there's very interesting approaches that can solve this with, in the short term, at least well enough to start to prove that the problem is like fundamentally worth solving for on-chain games. Another is obviously privacy. So zero-knowledge proofs enable this, but it introduces a lot of downsides. Oftentimes, to get privacy, you have to do client-side proving, which can be on the order of seconds, and you have to hold a lock on the shared state, which is challenging to do in the context of multiplayer games. So if you have to do a client-side proof, and it's 1 second, and you have to ensure that the global state doesn't shift underneath you, you now have like the synchronous proving overhead. And so like, what are some of the approaches that we can use to take advantage of this property of zero-knowledge proofs, but minimize the downsides? Like I think like one interesting one is incremental proving with recursive proofs, to be able to do some part of the computation locally, only enough to blind the inputs, and then pass that transaction onto a sequencer that can sequence it and execute, and commit to some transaction ordering, and then the proving overhead becomes asynchronous again. And I think there might be some interesting work in homomorphic encryption that could potentially be applied in this context as well. And then the other one is fairness, the final challenge. This is what I was mentioning, like in the context of if you have players that are participating in a dungeon and they're executing it fully off-chain, how can you ensure that that what they're doing is fair? They're not just throwing a lot of computational power at the problem. The numbers that they're using are actually random. They're not necessarily like rewinding time if they wipe, just do like a few steps before and then like running all the different permutations to figure it out. I think there's like some interesting applications of obviously verifiable random functions in this context. I think like a lot of the approaches today that I've seen introduce like a lot of latency and have a lot of overhead to generate random numbers, and we need ways to generate them with a much higher frequency. And then potentially verified VDFs, so verifiable delay functions for basically time scoping the run of an off-chain game. So if you think about in a game today, oftentimes you have like a casting time for some spell, and can you use like VDFs and some bounding on the time that you have to run an instance to be able to prevent people from basically trying all the different permutations, at least like add some computational overhead so that it becomes much harder to do that. Cool, so that's it for my talk, and yeah, happy to take any questions if there are.
Thank you for the talk. You mentioned kind of like 3 configurations of rollups. One is kind of like large scale, then medium scale, then small scale. Which is probably, and the small scale one seems like it's kind of a peer-to-peer, game session based sort of rollup. Do you imagine a sequencer, kind of like a central sequencer, still kind of sequencing user transactions in that small rollup scenario, or more of like a peer-to-peer?
Yeah, I think it's an open question, and I think it depends a lot on the relationship between the participants. Like if you think about just playing a board game at home, it's totally fine for you and your 5 friends to enforce like the ordering of transactions, just locally, right? Just like through you're just with friends, and if someone's going to cheat, then you're just not going to play the game with them. If you have, I think like there's potentially like 1v1 PvP types of games where actions can be very close to simultaneous, where there might be a little bit more contention on the ordering of things. So I'm not sure exactly the correct architecture for it. The Aperture guys that are here today have also posted some cool thoughts on their idea of battle servers, which I think is primarily like one versus a PvE, like you're playing just against the world. But yeah, I think it's a quite open question of like how best to sequence the transactions in that, and maybe a rollup is not like the best word for it. Cool.
I thank you for the presentation. So in the slide where you described the problem of fog of war, you mentioned secure enclaves as a possible solution. Can you explain more? What does it mean?
I'm probably not the best person to explain this. I don't know if Liron is here today, but he's been working on some research in this regard of basically using the secure enclave and attributes-based encryption to basically like conditionally expose information. So from my understanding, which is not very good, like I've just had informal conversations with him, anytime you submit a transaction, you would first submit it to the secure enclave, which would create some attestation that it's seen it, and then it would be sequenced on chain, and then like another participant can basically query a secure enclave given, like for example, an XY coordinate, and say like, do you know any additional information about this coordinate? And then the secure enclave would expose that if it meets the criteria.
Okay, thank you.
Cool. Thank you, guys.
Cool. Thank you, Tarrance.